Okay, right. So today's lecture is about web architectures. So we did basic HTML, CSS last week. Now we're going to pile on a whole load more programming languages, declarative languages, and how they connect through various hardware and software architectures. So the contents, well, we're going to introduce what is a computer architecture to start with, briefly. And then we're going to run through some of the various languages and standards that allow the World Wide Web to work. They're the sort of stuff that drives the World Wide Web. So last week we saw HTML and CSS, which is basically how to write a web page and design it. Today we're going to see a whole load more acronyms: DOM, XML, HTML, JSON, PHP, JavaScript, and AJAX. And that probably just makes our heads hurt to look at that list, but hopefully by the end of the lecture you'll have a picture of how all these work together. And throughout this, I'm going to give you an example, using as an example the Entangled Bank Integrated Database, which is a database that I built a few years back. It's pretty basic, web-based database, but it gives a good example of, well, it's a practical example that I was involved in building and indeed built that uses some various of these technologies and hopefully illustrates them in an applied manner. Just to remind ourselves, or to put it, the various components that might go into a web application, breaking it down, three basic things. We have data, which may be local or may be remote. So we talked in the first lecture, we talked about, the various crux, web map classification, local data, data that we own, that's our own. Might be called primary data. Can't say I'm a fan of the division between primary and secondary data. It's a bit ambiguous, but I'm sure you understand the difference. Everyone familiar with the difference between primary and secondary data? Primary data being data that you collected yourself, kind of. Secondary data being data somebody else collected. But if I collect primary data and give it to my friend, is it still primary data or is it secondary data? It all becomes rather a semantic thing. So we've got data, and we've also got logic. So what functionality does your web application require? And that includes things like the basic HTML that you provide, the sort of information that allows you, that describes the web application. But what functionality does your web application want to do? You've also got logic. Logic equals sort of programming here, programming logic. We've got the logic associated with the processing of requests. So you as a client, you've got your web app, you make a request. Somehow through the web application that gets sent to the server. The server has to decide what to do with your request and return something to you. So there's logic going on the server, and we'll go into more details on servers and clients in a minute. But we've also got the processing of the return, so the server returns something to you, and you need to process that in the browser. So there's logic going on both on the server and on the browser, potentially. And the other thing we've got is styling, which is basically how you design the interface that supports the functionality and makes it reasonably accessible. So you can think of break down a web application into those three components. So, computer architectures. Well, an architecture is simply the arrangement or relationship of parts that together comprise a complete design. Here we've got the Eiffel Tower and some of the plans, the architectures, the plans that went behind constructing the architecture that is the Eiffel Tower. The Eiffel Tower is made of bases, it's made of bits of girders of various sizes and shapes, and no doubt screws and rivets and all that kind of stuff. And you have to put them together in a certain way to create the Eiffel Tower. Well, in computers, computer architectures are very similar. You have to put various components together to create the thing that you're trying to create, your design. And we can think of two types of architectures. We can think of software architectures, what the software components are and how they talk to each other. And then we can also consider the hardware architecture the structures, the servers, the routers, the video cards, et cetera, that we might need to put in place to run our software so that we can run our software on top of that. We're only really considering software architectures here, although we'll obviously see a little bit about hardware architectures as well. So the simplest kind of network architecture that we can have is called the client server, and I'm sure most of you will have heard of client server architectures in the past and probably know exactly what they are. But we'll run through it again. So the client is your computer. Here, my computer, that's the client. Probably a web browser in this context, and I'm the user. So I interact with the web browser, the application in the web browser. The web browser, at some point, when I press a button or do a certain action, it's going to send some kind of request over the network to the server. And the server is just another computer somewhere else that's set up with a web server, Apache web server, maybe web mapping, other software running on it, that takes these requests, does something with them, sends me a response back to the client. Very straightforward. And I'm not going to go into the mechanics of that right now. So you basically got two machines. One is there sitting there waiting for people to ask questions of it, or other computers to ask questions of it and to provide responses. And the other one is me interacting with my web browser, sending the requests, and then the browser will respond on the basis of the response. And we can just put a sort of cloud like that in the middle, and basically client-server architecture, you can think of the internet being like that. Here's a server linked to the internet. Here's various clients talking to the internet. And the internet is just, as we saw in the first lecture, it's just a large network. That's all it is. It's just a large network like the network in Kingston University. It's just a very big version of that. So we can have multiple clients connecting through the internet onto servers. And indeed, we can create a sort of client-server architecture on one computer on its own. And that's what XAMPP is. So remember the XAMPP software that you can install onto your USB drive. So in that case, there's only one computer. Your server, XAMPP, is running on your USB drive, and your browser is making a request. Your XAMPP runs Apache's web server. So you're making a request from your browser to your local host, or the local host running on XAMPP, and that would return a response. So all you're doing is you've moved the server software from a different computer, and you're just running it on your own computer. Yeah. And we could respond that. I mean, you could put PG, for those of you who've done data administration and management, that could be PG admin 3, and that could be your PostGIS relational database. Exactly the same architecture. You've got a standalone server and some program making requests and getting responses off that server. One web client and one web page might involve talking to multiple servers. So here in this case, we've got our web browser client, and you're doing some development on Kingston. Well, this is indeed what you're doing for future practicals. So you've got your HTML documents and things, and your CSS files and your JavaScript files on your Kingston web server, StudentNet, or locally on your XAMPP server. So you make a request from your web browser, you request a page from your XAMPP server or your Kingston web server, StudentNet. It returns a set of HTML web pages, an embedded CSS style sheets, and potentially JavaScript. Okay, JavaScript we haven't talked about, but I'll go into JavaScript. JavaScript is the program that a program that will run in your web browser. So it sends you content and a program. Part of that JavaScript says go and get a Google map from the Google Maps server. So once you've loaded up this, it runs through the browser, reads the code, runs the code, and part of the JavaScript code says go and request some information, get some data from Google Maps, So it sends, the third action is to send a JavaScript request to the Google Maps server. API, I'll explain in due course, application programming interface. It's the language set up to, or the syntax that you use to query a online database. So you make a query for a Google Maps, and it maybe returns a map, an imagery, metadata. It could return a whole lot of different types of information, and then that gets incorporated into the map, into your page, your content that you've defined in HTML. Is everyone okay with that? Okay, so you're just making one request, getting some information. The information you get back says make another request, and it could carry on and on and on. You could have dozens of requests potentially. So this slide just kind of summarizes, well, it's just an indication that sort of how clients and servers differ, because they do generally differ. One is set up as a server to process requests, and the other one is your everyday computer machine. So, for example, the hardware of a client is usually a PC or a laptop, whereas a server, okay, it could just be a PC that's had server software installed, but increasingly, and in places like universities, there's a room with lots of cabinets and buzzy lights where they stick in another, what they call server rack, which is a set of disks. So it's a sort of slightly different hardware configuration often with servers. But a server can just be a computer. You can run any computer can run as a server. If you've seen those pictures of Google data centers and things like that, that is a massive server that they've got, whole buildings full of these server racks, storing vast amounts of data and serving large amounts of information over the internet. You run generally different software on the clients and the servers. So on your web clients, you're running a web browser generally, Explorer, Firefox, Chrome, whatever tickles your fancy. Whereas on the web server, you're running Apache, which deals with the requests coming in and forwards the data to relevant programs to run the relevant programs that then gives the data back to the Apache that sends it out to your computer. So Apache on web servers are basically the gateway for the server. The server is the sort of, you're making a request to the server, it goes into Apache, and Apache decides what to do with it and how to process it. Presentation, well, okay, so it displays HTML. You run different, we'll look at the logic, we'll ignore the presentation there. But the logic, so on a web server, you generally write your logic, your programming logic in PHP or a language like Ruby or Python or Java. Within a web browser, often it's JavaScript, but it can be action scripts, it can be Java applets embedded in web pages. There's a whole variety of ways that you can, different languages that you can write programs both on the server and on the client. So that's sort of a basic introduction to layers. Now, to architectures. Architectures are often described as layered. Okay, so we've seen some really basic, simple server, different versions of client-server architectures. And as I say, they're really basic. So the idea of a layered architecture, so okay, the idea of software architectures in general is to separate functionality into separate modules that you can then put together to create your application. Okay, so it's a modular design principle. So you have a web server that produces, or a map server that issues maps, and then you maybe have a web server that deals with basic HTML, and maybe you've got some other bit to do with visualization. So you keep things modular. And a layered architecture is where the modules share a sort of common function and can be ordered into what we call logical layers. And I'll give you an example of these, so don't worry, this is a bit obscure. So basically, you've got these software modules, and where they do similar things or function in a similar kind of context, then they can be ordered into logical layers. And here's an example. Sorry for the quality of this one. I've got some better ones in due course. So here's an example of a three-layered typical three-layered architecture. So here we've got, at the top, we have our client layer, what we call our client layer, which is your web browser on your personal computer. So you've got maybe JavaScript running there. You maybe got Java applets embedded in your web pages. It's where the HTML is read and interpreted and displayed. We then have a layer which we may call the web server and the application server layer, the application layer. So this is on the client, these two layers are on servers. So you come in here, the web server, your Apache web server, that's what your web browser communicates with. It communicates with that, with the web server, and then it maybe passes some information to an application server, which is basically your program written on the server, which may then request data from a relational database or potentially from something like Esri shape files or CSV files. So we can separate the logic on the server from the data on the server. So we end up with a three-layered architecture. We've got a layer of data, we've got a layer of server logic, and we've got a layer of browser logic and browser display. And we can organize these things. We can see that we've got different functions in each layer. These are all up, obviously, online, so please don't draw the pictures. So let's have an example of that, kind of. So my last job before this coming here, I was given this data, basically, a phylogeny, which is an evolutionary tree of all mammals, a taxonomy of all mammals, a database, just a flat file database of the traits of lots of mammals, their body size, their weight, how many offspring they have, what their gestation length is, all that kind of lots and lots of variables. I had range maps for all the mammals from the, they were collated by the WCMC, which I can never remember what it stands for, as in Cambridge, and something called the Global Population Dynamics Database, which was a database of abundance records for lots of different species around the world. And that's a sort of 3D viz kind of attempt to visualize those data. So I had the job of putting these data together into an integrated database to allow people to query across these data sets. So to do that, I built what's called the Entangled Bank Integrated Database. It's online, you can go and look at it. It is not the most sophisticated online database. It was the first web database, in fact, only web database I've ever built, that's certainly of this kind of size. So it's a bit basic, but it actually illustrates, because it's a bit basic, it actually illustrates, to a certain extent, the web development process. Doesn't matter about the fine details here. This is just throwing the front flash screen, but you can decide which one of those data sets you want to query. What does it look underneath? Well, underneath, all the data is stored in a Postgres database. So we've got tabular data, just normal relational tabular data. We've got the spatial data, the range map, stored in PostGIS, in the PostGIS extension to Postgres. You're happy with what a relational database is? Yeah, good. Okay. We've got the trees stored in a database schema called PhyloDB, which is designed to store networks, not spatial networks, but just aspatial networks. I used, it doesn't matter what BioSQL is, but BioSQL is a database schema for storing DNA and protein data, but I merely used it as an ontology store. An ontology, a list, is where I store my lists of controlled vocabulary, so lists of words and things like that. You can only put these words, use these words in this context. It doesn't really matter the details of it. And the GPDT time series. So we had a data layer, which is basically my database, my Postgres database. Then I can access that database either using client software. So for example, pgadmin, I can write SQL queries in pgadmin, or I could connect using the open source Quantum GIS. So if I'm an expert user, I can go in that way. But we can ignore that, because what we're interested in is the interface, the web interface. So I built a web interface. It's the server-side logic is in PHP. The browser logic's written in JavaScript. I use the GDAL OGR library to translate between geographical data formats. So if I want to output, if somebody wants something in shapefile, I use GDAL to convert from the PostGIS into a shapefile. They can also export it as a map info file or a GML file, geographical markup language. At one point, not anymore, I was calling some Perl code, and I have a mapping interface onto this to allow people to make spatial queries using the map layers JavaScript library. And this allowed non-expert users to make queries of this database through the web interface. As I mentioned there, the web interface, the mapping in part of the interface, because the mapping side is only a small side in this application, uses the Open Layers JavaScript library, which is a very powerful open source map client. Supports zoom, panning, adding user data, different base layers. So for example, you can change between showing the Google Maps layers to change it to the Microsoft Bing layers or OpenStreet layers relatively easily. There's little tools that allow you to toggle between those. It also allows you to develop on mobile devices and indeed 3D mapping, not that I used any of those functions. So this is what my simple web interface looks like, and it's quite clunky, I admit this. As I say, it's the first one I ever built. Also, unfortunately, the day I took this screen dump, we got this metadata window started appearing in the middle of it for some reason. And so this is not meant to be there, I hasten to add, but that's life. So this is my little interface. So it allows people to, we can see we've got the Google Maps layer here. It's just the Google interface layer. You've got a panning, you can pan, you can zoom, you can, but this is the important stuff for me. So a user can put in a polygon or a line or a point, and then they can use that geometry to make a spatial query. There's a whole variety of operators, spatial operators that are supported by a pull-down list here. So in this case, I've got a polygon drawn across part of China. We've got the within polygons operator set, so that when you run this query, what it's going to return is all the ranges, mammal ranges, all the global population database points, point locations, and also the bounding boxes. Don't worry about the difference. Basically, there's two types of geometry associated with the GPDD. There's point centroids, where we think, so for example, we may have the population of a lemur in Madagascar. So we have a point in the center of Madagascar, but we also have a bounding box around Madagascar as well. You can search on both those. But it will go away basically, and it will search for all the mammals within that drawn polygon. You can also add a bounding box with defined coordinates down in this little section. And this is a diagram of the architecture behind the entangled bank, a bit more detailed. I just drew it the other day, and I'm sure it could be tidied up a little bit. But let's just run through this, because we've got 3 computers here, or more than three servers. So we've got a client up at the top, your web browser that you're accessing the entangled bank website. And we've got HTML content, CSS design, and JavaScript logic. So the first thing that happens is that this is regarding the web mapping interface, is that the user makes an HTTP request to the entangled bank web server, which is my Apache server here. When they make the request, what it does is it runs a server-side program written in PHP. We'll go into that in more detail in due course. And that program, depending on what the user request is, writes HTML, writes CSS, and writes JavaScript. And it may make queries to the database and process the data returned from the database. Okay? It may also, depending on what the request is, if it's a return data request, it may get the data out of PostGIS, the spatial data out of PostGIS, and then it might call the OGR library to OGR library to do the format translation. So from going from whatever the database returns to going to a shape file. It would send the data in here, get the data back, embed the shape file, return the shape file as part of the HTML file returned. Occasionally it also calls some Perl script. Don't worry about that. So that's running on the host server, which runs actually on the Imperial College, one of the Imperial College servers up in London. So we've got the client computer, the client layer. We've got the server logic layer with the Apache server, my PHP programs. I've got my database layer, which is actually on a host server, which is in a different machine to the server here. Doesn't really matter. So the database is in one place, the logic is in another place. If it's the web mapping page that's returned, so from our first HTTP request, if it's the web mapping request page that's returned, then that includes that Open Layers interface. The Open Layers interface code is hosted on the Open Layers server. I haven't made a copy of it here. I just call it from the Open Layers JavaScript, and they return the JavaScript library. So the second request, so once the first request has gone through, if it's the mapping page, it goes to Open Layers and gets the Open Layers library from there. If it's the mapping page again, we then need some data. So the Open Layers JavaScript library then calls the Google Maps API, which calls the Google Maps database, which returns the maps that get embedded within the page. Don't worry if you're going, at this point. That's kind of the overview of how the system works. And we'll return to that in due course. Thick and thin clients. Thick and thin clients is a term that existed mostly, I would say, about 10, 15 years ago, and still exists, but to me it's kind of almost historical. But basically it describes how much processing logic, or how the processing logic of an application is distributed between the client and the server. So a thick, fat, or rich client has lots of local processing. So it's all going down on the client. And one description of thick clients was internet-enabled desktop software that talk to the web, but can also read and write to your hard drive. If you're familiar with UDIG, has anybody played with UDIG? UDIG, go and have a look, download it, is an open source GIS program that specializes in web data manipulation and integration. So you download UDIG onto your local computer, and then you effectively start accessing web map, web feature service layers. Don't worry about what they are. We'll talk about those next week. But also, if you have lots and lots of JavaScript being sent to your browser and functioning in your browser, or Java applets embedded in your browser, to me that's thick as well, because all your processing is being going on the local client machine. In contrast, a thin client runs within a browser, no installation or download required, runs through JavaScript and Ajax. We'll talk about those in due course. Small code base. The Entangled Bank is an example. So the Entangled Bank, it's a little JavaScript mapping application. That's all it is. There's a small amount of JavaScript sent to your browser. It's very low effort. There's not much processing to be done, not much code to be sent. So basically, to me though, I'm a bit confused, because sometimes you could have a thick client application. You could have lots of stuff going on the server, lots of stuff going on the client. Is that thick or thin? Okay, so that's the architectures section, and we'll go back to architectures in a minute. Now, what we're going to do now is just run through the various languages and standards that help all this architectures talk to each other. How does this actually occur from a software and data perspective? So the first thing I want to do is to just, first slide just sort of clarifies what there are two types of things that are called languages or programming languages, two types of languages. And what's the difference between a language, what is a standard, and what's the relationship between them? So the first thing to point out is that there are two types of languages. There were what are called declarative languages and imperative languages. And those who've done data management will hopefully remember this. Declarative languages define content, what is or what must be done, but do not specify how that is to be achieved. HTML is one. HTML defines what is displayed on the web page, but it does not say how to display that, merely what is displayed. And, well, it defines it as in how it is arranged, but it's not telling the browser exactly how to do that. The browser has its own logic. When it sees an HTML file, it reads in an HTML file, it decides how it's going to interpret that file to display it. Okay. XML, JSON, another examples, we'll see them in due course. One other one you might be familiar with is SQL. SQL defines a query, but it doesn't tell the database how to search through the data tables to extract the data. Imperative languages define the steps required in order to achieve the desired outcome. This is what you would normally think of as a programming language. Python, PHP, Java, C, Python, JavaScript. You tell the computer what to do, okay? And, you know, to be honest, it doesn't matter whether you remember that SQL and HTML are declarative languages or not, but it's kind of useful to know the difference and recognize that these are, in fact, different things. So what's standards then? Well, standards are just agreed ways of specifying or doing things. And they tend to be managed by consortia, groups of companies, individuals who have a historical stake in a particular set of technologies or things to be done on the internet. So, as we met before, the World Wide Web is managed by the W3C consortia, which is run by, ultimately, I think, headed by Tim Berners-Lee. So they define how the World Wide Web works, what the standards are. They define HTML. That's what they do, among other things. And for geographic data, it's the OGC. I never Open Geodata Consortium. I can never remember. You know me, I can't remember any of these titles, what they actually are. Open Geospatial Consortium. And standards, why do we bother? Well, if we don't do things the same way, our software and our hardware can't talk to each other. So it enhances interoperability. If we all do our things in our own way, then we can't talk it's more difficult to talk to each other. If we all follow the same way of doing things, then hopefully we can exchange information and data relatively freely. Most standards concern declarative languages. So standards and declarative languages go together. Interpretive languages and standards, I've never really come across any that are particularly, closely linked with interpretive languages. HTML and SQL are standards. So is XML, so is JSON. Those are all standards. And one of the important things to remember is that while many software sort of support standards, very few actually support all components of standards, and they vary greatly in how well they comply to standards. So even something like PostGIS, the Postgres database, which actively pursues being standards compliant, SQL standards compliant, is not fully standards compliant because of historical things. Okay. HTML DOM. So this is our first standard. Right? So what is the HTML DOM is called the document object model. And this is the WC3 standard for representing and interacting with HTML documents. Remember, you've got your HTML document, you've written it as a text document. It gets loaded up into your browser. So your browser accesses an HTML document. What it does is it reads the code, and the code gets read into the DOM. So the DOM is sitting in the browser, and it's a computer structure that stores the HTML document. And it's the product of the late 1990s browser wars, and when JavaScript started arising. Basically, Microsoft were doing their thing. Google in this day, didn't even really exist at this point. Well, it did exist, yes. So we had Google Chrome coming in then, and then we had the likes of Firefox. Basically, they were all doing their own thing, and there was a great scrap. Everybody was trying to win. Microsoft started wrapping up their browser with their operating system. They ended up in court and told to get to separate the two, et cetera, and that stimulated. Basically, they eventually agreed that they needed some standards to prevent this, because it was wasting everybody's time and effort. The DOM is a hierarchical tree model of a web page. Remember, last week we had the HTML, and then underneath we had the head section and the body section. So immediately we've got the HTML, and then we've got the two leaves underneath. And browser languages access and edit the DOM. So JavaScript, how you move things around on a web page with JavaScript is by editing the document object model. And here's a picture of it. A document has the root element HTML. Under that, you have a head section, which maybe has a title, which maybe has some text with the title. Here, on the other side, the body section, maybe you've got an anchor link, you've got a header link, you've got text associated with those, stuff like that. Okay, so that's a just very general picture showing the hierarchical structure of the DOM model. Strict transitional HTML, actually I did this last week, so we don't really need to go over this. But as we know, HTML originally mixed presentation with content, and then when CSS came along, it separated content from presentation style. Basically, strict HTML forbids presentation syntax. All the presentation has to be in CSS. Transitional HTML allows you to use things like bold and EM and I tags in your HTML. Markup languages. So what's a markup language? A markup language is a language that annotates text so that a computer can manipulate that text. And you saw one example, hypertext markup language. But there are also other ones, XML, we'll see that in a minute, XHTML. And most markup languages are human readable because the annotations are written to distinguish themselves from the text. So they're quite, you can read through them, just read through and see what it says. So what's HTML, XML, and XHTML? HTML we've seen, it's a standard vocabulary. It is a declarative language that defines what elements you can write. It defines A tags, header tags, anchor tags, image tags. They are defined. You can't create your own HTML tag and start using it, adding it into HTML. It doesn't work. It's a defined set of words or tags that you can put in your HTML documents. It's also not very strict in that the browsers in general are quite tolerant of people forgetting to close their tags and do things like that. XML is a syntax standard. It is not a vocabulary. It is a standard for defining how you write something, not what you can write. Okay, I mean, it might not be immediately apparent what the difference is. XML stands for extensible markup language. So it defines how you write data, not what you can write. HTML defines what you can write. And XML is an example of a meta language, and you can write your own XML flavor using the XML standard syntax. Okay, that's probably just going over your head at the moment, but we're going to see some examples of these in a moment. XHTML is the HTML vocabulary that follows the XML syntax, and it is also called well-formed HTML. We don't need to worry about XHTML at all. XML, extensible markup language, and it's used for storing and exchanging data and documents across the web. And it's part of AJAX, which we'll see later on. So HTML and XML are both markup languages defined by tags, but they have different syntax rules. For example, XML elements must always have an end tag. HTML elements don't have them. XML tags are case sensitive, so capital catalog is not the same as catalog lowercase. And XML elements must be nested properly. So they've got a strict syntax. XML has a strict syntax. HTML, you can get away with a bit of looser activity. And here's an XML file. XML version 1, just like the beginning of your HTML file, it defines what version you've got. This is an employee database. Employer, it's database. You've got a tag employee. In fact, we've got 3 employee tags, and embedded within each employee tag, we've got a tag for the name, a tag for the country, and a tag for the age. And we just carry on that, and that defines a flat file database. Yep. We've got columns, name, columns name, column country, column age. We've got 1, 2, 3 employee records. So that's an simple employee database in XML. If you wanted to, you could easily put a new tag. You can put a new tag in there saying gender, male, female, not stating or whatever. So you can add in any tags you like of your own use that you've defined to meet what your needs within that XML file. Unlike HTML, where you can't add your new tags in. We won't bother with XHTML, and we won't bother with HTML syntax because it's too not worrying. However, I'll just show you this. This is an online. If you want to turn your HTML into XML online and to check the syntax is correct, you can do with various online validators, and you'll do that later in one of the practicals. But we'll stick off that. JSON, JSON. That stands for JavaScript Object Notation. And it's like XML, and it's used to define data, but it's if you remember that XML file, there was an awful lot of extraneous information. We were defining employee tags, we were opening and shutting tags. There's a lot of unnecessary text in there, filling up space, taking up extra room, leading to slower file transfers. So this is just a sort of similar thing. Here we've got a similar set of information. We've got a first name. Notice we open and shut with some curly brackets. First name, John. Last name, Smith. Age, 25. Address. And you can see we can put a hierarchical type of syntax here to define various types of information. We've got 2 sets of phone numbers. So we've got 2 types of phone number for this person. We've got an address with various tags for the address. But you could see that data could be written in XML, and we could have taken that XML file and we could have written it in JSON format. Yep, just alternative ways of writing the same, of stating data. PHP. PHP, which stands for Personal Hypertext Processor, is an example of a server-side imperative language. So a normal programming language. But you could also write server-side code in Python, Ruby on the Rails, many other languages. And it defines server-side logic. As I said, with the entangled bank, that was written in PHP. When everybody makes a request of the entangled bank, it runs a PHP program. That's what they're doing. They're asking the server to run a PHP program. And generally what these do is they dynamically write HTML depending on what the request is and what the context is, and also the styling and the JavaScript, and a lot of database query. And PHP scripts can be embedded in HTML. PHP and HTML were developed kind of together, and PHP comes as default language with Apache and things like that. So we can write code like this. We can embed PHP in HTML. So here's our HTML document that just says, hello, today is, and we want today's date. How do we get today's date? We run a little PHP program. Echo just means write to the screen, the date, and then we've got a format string for telling us how to write that. So that means every time that web page is loaded up, it tells you what the day and date is. APIs. APIs are application programming interfaces onto a database or another web resource. And we'll concentrate on databases here. And it allows a client to request data from the database using a published query syntax. We'll see an example of that in a minute. And the data is returned as XML and JSON. So this is where JSON and XML come in. You make a request to a web server, to an API to return some data. It goes and queries the database, returns the data, and the data gets returned generally often as XML or JSON format. And it's called AJAX when it's called from JavaScript, and we'll see that. Yes. So here's an example, Global Biodiversity Information Facility, which is a portal that provides museum records from all around the world. So it's a global portal and to multiple museum databases around the world. And they have a web service API, which is defined on these pages. So that's just the main GBIF page up here. Here's the definition for the web-based API. And what I can do, or what I did this morning, was I stuck in, there's my web request in the top there, api.gbif.org/v1/species, match, question mark. So this is the query that I'm sending, and I'm asking that it to return data it has on species that match, that have the species name Ephippigera ephippigera. That's my bush cricket I've worked on in the south of France. So that's why I'm asking for some strange little bush cricket name. And here is, what's that? Format's that? JSON. It's given me a JSON return. That's it. I can type the query following the syntax, the API syntax, into my web browser, and it returns me a JSON file with all these fields about the fact that it's a Tetigonidae bush cricket and what its genus is and all sorts of stuff like that. That's just a really simple aspatial example. JavaScript. JavaScript is an imperative language, so a sort of normal programming language that runs client-side in the web browser. So PHP on the server, JavaScript in the web browser. Unrelated to the programming language Java, no relationship to them at all. Java and JavaScript, totally different things. And the code is defined server-side and embedded within HTML script tags. So the HTML has script tags, and you embed your JavaScript just like you embed your CSS in your HTML with your link file. It allows interactive manipulation of the document object model. So you can add a new header. You can delete it. You can change the CSS. You can actually programmatically change the CSS. And then you can create animations that way. You can redo the text. You could change the text in some form or fashion. You can do lots of things. And it also supports really complex graphics. And that's one of its great things, not only manipulating and changing the web page in the browser, but also complex graphics. It's lightweight, but when combined with XML, becomes a very useful tool. And we keep seeing this word AJAX. We'll actually get there in a minute. And for example, use JavaScript to overlay custom markers, lines and polygons on top of Google Maps to create a mashup. And indeed, the web interface with on the entangled bank where you enter the polygon, that's a JavaScript application running in the browser. And there are all sorts of alternatives, ActionScript, Java applets. So this is the final thing. We've been building up to what Ajax actually is. Ajax is asynchronous JavaScript and XML. That's where the word Ajax comes from. But the Ajax kind of principle can work with JSON files. It doesn't need to work with JavaScript. So it could be ActionScript and JSON. But it's just it was first described with JavaScript and XML, and that's stuck. And it's a very important method for client-side architectures. And basically what it is, it supports background requests from the browser that do not require reloading the HTML DOM from the server. Okay, so if you request a web page, you type in your URL, it goes away to the server, finds all the web pages, all the JavaScript, all the CSS, sends it back. That could be quite a lot of code if it's a big application. Now, if you just want to say, okay, give me a list of cities in Germany or something like that, then what you don't really want to send that request into the server, reload all the pages, reload all the JavaScript libraries. You just want to get that little bit of data. And Ajax allows a browser to make a quick request. Oh, I think we're running late here. A quick request and return a small amount of data as a JSON file. And that makes for much smoother web-based applications. So a traditional architecture is like this. Your user interface, you make an HTTP request, you generate the pages, it gets returned, the HTML and the CSS gets returned, gets displayed in your web page. An Ajax system allows you, once your page is loaded up, to make a little JavaScript call, which makes a query of the web server, returns a little bit of data that incorporates it into the pre-existing document object model. So it just allows you to say, give me a little bit of data and add it to my screen, do something with it. And what that means is that you get a much smoother user experience. So under the classic web architecture client server, the client looks at his web browser or their web browser, does something, asks for some data, makes a request, the server does something, system processing, returns it to the user. The user sits there waiting, does nothing while the data's coming back. Then they look at the results, they make another request, they sit there while the server returns the data, they make another request. With Ajax, once you've got the initial page loaded, basically you can make requests, and then in the background, the JavaScript will make the request of the server, return the data, and the user can carry on making these little requests all the time, and the browser's constantly getting little bits of updated information from the server. So basically, the user activity is continuous, and potentially there's lots more server-side processing. So it results in a much smoother user experience. Ajax and the entangled bank, well, I only got to Ajax near the end of my employment, so most of the entangled bank runs on client-server architecture and posts and is not the most efficient and beautiful system the world's ever seen. But I did implement a small bit. There's two places where Ajax was used. One is nothing to do with me, but Ajax is involved in open layers. Open layers comes back with a JavaScript library and then makes a request of Google Maps. Well, that is an Ajax response. That is JavaScript and browser making a request from the Google Maps server using an Ajax architecture. But I did actually implement a small amount of Ajax that allowed, for example, simple search facilities. So a user wanted to get a quick list of what species were in the database. They could make a quick Ajax search, get that list back up. So I did implement a small amount of it. But the majority of the database remains a simple client-server architecture, and then as a result is slightly clunky, is rather clunky. But it works and it does things that no other online database does, which is good. Okay, so finally, I think I'll probably blow said put too many acronyms in your head for a Monday afternoon. So what have we done? We've looked at architectures, client server, distributed Ajax architectures, layered architectures, thin and thinner clients. So various words and terms used in relation to architectures. And then we've looked at the various components that put together make up this, allow the internet architecture to run. So we've got the various languages, which may be declarative or imperative, may run on the server, may run on the client, may define content, styling, or logic, and that the standards, following the standards, enable interoperability. And we've seen the entangled bank and how those technologies were put together to create a simple web-based interface. And here we see what is the entangled bank? Well, it's got a three-layered architecture, client, server, and database. It's basically a thin client. It just runs on a little bit of JavaScript doing the map window. And it uses, basically, it's built in with a traditional web architecture, but with a tiny little bit of Ajax added in just to add a bit sort of icing on the cake of the functionality. The languages required to write the entangled bank were HTML, XML, PHP, JavaScript, a little bit of Perl, and calling an executable C program, SQL, including Postgres functions. So there's about 7 languages involved in building that web application. And the standards involved, well, not a huge amount, but the database schema standards, BioSQL, PhyloDB, and PostGIS standards. And then when it comes to the web stuff, HTML, XML, we know about, but also a format used internally called well-known text format, which is a WC3 standard for representing geographical data.